us about how Rhino can work with Flower to accelerate adoption of FL even further. So over to Tal. Thank you for joining us today. It's really great.
Great to be here. Since we're at Flower Summit, gross simplification would be to say we do take care of all the boring enterprisey stuff that needs to happen to make federated learning practical at scale. Our Federated Computing Platform, or FCP, is a distributed system comprising a cloud and many clients distributed around the world, and it provides graphical and programmable interfaces, manages the clients, orchestrates workflows, enforces permissions, tracks all the actions to provide auditability, and much more. And of course, it never stores any row-level data in the cloud. So why have we built this? What does it actually take for federated learning and compute to be enterprise grade and scalable? So we've learned this by doing it, where today our platform is used by dozens of healthcare organizations around the world, many leading biopharma companies and large global financial services. And the table on the right shows some of the things we found need to be done differently in an enterprise setting. So for example, you need flexible managed installation of the clients in various environments. You need to address governance concerns, first-class support for automating workflows and integrating them with other systems. You need support for many different types of federated compute workloads, such as data preparation, federated inference, federated analytics. You need to address scalability, and you need to support the needs of many different kinds of users, not just research scientists, and the list goes on. So we provide an end-to-end solution for the entire federated computing projects and workflows, and you can use any component individually or use several together for a powerful combination. So here's one example workflow. To begin with our harmonization copilot, you can use a GenAI-enabled federated tool to harmonize data from disparate data formats into a single common format. So we have out-of-the-box support for common models in the world of healthcare, such as FHIR or OMOP, but you can also harmonize to any custom data format that you need. You can also take data from several sites or just one and create data catalogs, which others can browse in a federated and secure way to perform feasibility analysis, understand where there's data that's relevant to my project as a data scientist. This uses federation and privacy preservation, making sure the underlying data and access to the analytics are protected by our permissioning and adheres to the principle of federation, where the underlying data stays at rest at the original site. Once you have the data, you want to actually run your federated project. Now, federated learning is awesome. We all love it. That's why we're here. But usually you need to start much before you're ready to train your model. You need to analyze your data, perform exploratory data analysis. You need to pre-process your data. So you might need to annotate your data, and you can do that on our platform too, either with built-in annotation tools or bringing in whichever annotation tools you're already using and use them on the platform. When you finally do get to modeling, you'll likely need to run a bunch of experiments to try different models, different model combinations, hyperparameter tuning, and so on. And all of these are supported out of the box, where specifically for federated learning, of course, you can use our integration with Flower, which we're big fans of, and you can use Flower to train your models in a very seamless way. Then once you have your model trained, you will want to evaluate it, and you can do that on platform too. We have a wide library of federated analytics tools built into the platform, which you can use to analyze data, again, in a federated and privacy-preserving manner, including some novel federated implementations of common metrics and statistics. You can also perform custom visualizations, either using third-party applications like Streamlit or any software you like, Matplotlib, Seaborn. We also support using any custom application you want to interact directly with the data. So, for example, if you're using medical imaging tools like 3D Slicer or QPath, you can do that to view medical images. So as I've been mentioning quite repetitively, the Rhino Federated Computing Platform is tightly integrated and easy to use, but it's also at the same time super flexible where you need it to be. Client installation environments, data sources, and all the software tooling used to work with data and models. Every workflow and project can use the best tools for the job that needs to be done, which are usually the tools you're already using. And thanks to being a persistent, always-on system, you can integrate it and automate it, using our API and SDK. All of this is done in a federated manner on an enterprise-grade platform that makes sure to take care of all the details. Now it's time for a live demo. I'm hoping, with all the technical difficulties and Wi-Fi not working very well today, that this actually works. Let's try it. It's supposed to. I tried it earlier, but you never know with these things. And wow, that is very, okay, I'm going to look over here so I can see what I'm doing. So I'll start by signing in. You can see we have support for SSO. I'm just going to use my password manager. If it actually, okay, there we go. Let's sign into the platform. This is our demo environment. All right. So let's start by looking, I mentioned data harmonization before, so I have a project here, like this is all with dummy data, not real data. So I have a project here set up for harmonization, and so I have, let's look at the data schemas page. So I have several tables of data which I've made available on the platform as data sets, and I want to harmonize these, in this case, to OMOP, so to several OMOP tables. I'm going to do that using data mappings. So we have, this is what I mentioned earlier, with an on-platform tool that is GenAI based, but human in the loop, and entirely no code, with a graphical interface. So here we're going to create mapping. So we have, this is comprising, the mappings comprise two main parts, which are syntactic and semantic mappings. Syntactic mapping, so in this case, I'm going to map my data to OMOP. If I click in, I can see what this looks like. So I am mapping source fields to target fields in the OMOP domain that I'm targeting. And I'm defining transformations for each of these fields to bring it to the structure it needs to be. So for example, sometimes I want a stable UID, sometimes I want to have a custom row level code to just transform something at a row level, and sometimes I want to do what we call semantic mapping. So what does that look like? Let's head back. And I have an example of that ready here. I'm very short on time, so I've prepared everything in advance. If anyone wants a more in-depth demo, we can show all this in depth with more time. So for example, if I want to harmonize, I want to transform the procedure name to the OMOP procedure domain. I can use this interface to define that mapping. So how to map every source value that I have in my data set to the correct target value in the OMOP domain, the OMOP vocabulary. And this is where the LLM comes in. We run a local LLM on the client that generates suggestions for the target value. And this can be reviewed and just repeat this. And this allows someone who's not technical at all, like an expert, someone who's an expert on medical informatics, to do this by themselves without any technical support, directly on our platform as part of a bigger project. Once all of that's done, so I have this mapping, it's a syntactic mapping that uses some semantic mappings. This is automatically also represented as what we call a code object. This is a runnable ETL that can transform data from one form to the other. I just click run. And I can select these tables, these data sets local that I want to transform using this, hit run, and those will be transformed into new data sets, new versions of the data sets in the target format. Now, once I've done that, maybe I want to share some of my data or make it visible so people can discover that. So we have what we call federated data sets. This is a catalog of data sets that users on our platform have created and shared. So anyone can view data sets on our catalog, see some information. I can search these, I can query the data, and this is with permission. I can also view analytics and bring these data sets into my project so that I can continue to work with them. But now let's move on to computation. This is what we're mainly interested in here today. So I'll head back to the projects page. Hopefully it loads a bit more quickly. Okay, so I've set up we have a demo project here for pneumonia prediction. And in this case, we have a few data sets. We'll see a few more data sets that have gone through the processing because I've done this in advance to make things go more quickly. So I'm starting with 2 data sets, each on a different sites that are collaborating on this project. And I want to, let's first take a look at these. So if I head over to analytics and I'm going to select, once this loads, I'm going to select just those initial data sets. All right, what just happened now? This is federated analytics. The data for this is not on the cloud. The data for this is on the client, and queried each of the clients, collected the secure aggregated statistics from each of the data sets, and it's showing me the aggregation of that. And this is provided automatically. You can also do custom analytics using other tools. So I get this sort of out of the box. I can see the approximate distributions of different fields in these data sets, and I can see also a completion table. But let's say I also want BMI. I have height and weight, and I want to add BMI as an input. Ooh, wow, I'm not going to be able to show everything I wanted to. So I'm going to skip over a little bit. What I do to run computations on the platform is I create a code object. So if I want to add BMI, I can just say, okay, this is a Python code object using a certain version of Python. I enter a snippet here that adds BMI. And then once I've done that, I have this add BMI code object. I hit run. That creates a code run that accepts data sets as inputs, creates new ones as outputs. And the same way I can do imputation, I can convert images to other formats, and I can create a code object for training a model using Flower or NVFlare. In this example, I used NVFlare. And in a very similar way, I would just click run, select the input data sets that would trigger the training. I can click into, like during or after the training is run, I can view all the configuration details. I can view the logs from the server and from the clients. This is also done federated, protected by permissions. The client-side logs are stored only on the client. And then once I have my model ready, so again, during or after the run, I can open TensorBoard. We have a special integration of TensorBoard on our platform that is also federated and privacy preserving. And I can see details. In this case, these are TensorBoard logs from the clients, where I can see and I can compare data from different runs, different training runs, or from different clients in the same run. I have all the power and flexibility of TensorBoard at my fingertips. And then all I need to do in my code is, like, I just use TensorBoard as usual, and I get this out of the box. So yeah, I'm over time. I'm going to summarize and just say, this is not just a single workflow that we support end-to-end. Like, you can combine these pieces, and like we were just scratching the surface, there's a lot more, to combine them and to do whatever, basically anything you need in a federated way that is enterprise grade and scalable. Thank you very much.
Great demo. I think we're going to move on, but sure. Folks can talk to you in the break to find out more, maybe see more of a demo. So thank you so much.
Thank you.
Yeah.